questions about anything from last time? About anything? I'm going to talk more about what Fourier series converge to today, and play around a little bit with Johann's solution to the harpsichord problem to motivate full Fourier series. Full Fourier, so that's the Fourier sine series there. F of x is a sum of wiggling sine functions, is the expansion. Because they're orthogonal, those ANs have to be given by the integral there. And the Johann's solution involved that Fourier sine series. The only addition is the multiplication of cosine nt in each of the terms in the infinite sum. And I put equal with the quotation marks there because we're not totally sure what that series. We know it, in the case of the harpsichord problem, it converges to something. And we would hope that, and we saw that that something is probably f by playing around with maple, but we don't know that yet. Soon we will. Oh, by the way, homework 2 is due tomorrow night in Gradescope by 11:30 p.m. What's that? Oh, homework 1. Nah. What did I do? Okay. Yeah. And to try to cut down on the number of late papers that my grader has to deal with, I'm just not going to allow late papers without prior permission. So if there's some reason that you need an extension due to illness or something like that, unless you talked about that with me beforehand, you'll find that you get locked out of the turn-in portal. So be sure to get it in by 11:30 p.m. Okay, any questions now? Yeah.
Gradescope says homework 2 is due next Thursday at 11:30 a.m.
Well, that's a mistake. I'll fix that. God. Seem to have problems with those buttons. Thanks for catching that for me. Yeah, so let's see. I want to think about more what this thing what this converges to, and one way to see what it converges to is to further consider the difference between Johann's solution and his brother Jakob's solutions. So here's some important trig identity. Funny how many trig identities come up in Fourier analysis. Every one I ever heard of, basically. The famous trig identity is that sine alpha cosine beta is equal to 1/2 sine alpha plus beta plus sine alpha minus beta. That's not hard to derive. You take the sum of angles formula and play around with it, and it's quite easy to deduce this trig identity. You probably had to do it when you took a trig class back in who knows where. 8th grade probably. Or maybe that's 11th grade, I forget. Anyway, using that trig identity, look what I have there. I have an alpha and a beta in my Jakob's solution. So this is Jakob's solution. I'll call this thing right here alpha, and this right here beta. And so I'm going to show you here that Johann's solution implies Jakob's solution, because of this trig identity. And in fact, it leads to something interesting when you start thinking about Jakob's solution. Let's see, so what do I get when I do that? I get u of xt is a sum, it then goes from 0 to infinity, of 1/2 an sine of nx plus nt plus sine of nx minus nt. And interesting, let's see, so let's call this, let's see, what is this? This is n times x plus t. And this is n times x minus t. Okay, so if I call x plus t a theta, I'll call that theta and psi. So let's call this theta, and let's call x minus t psi. Then we see that this is 1/2. The sum as n goes from 0 to infinity, an sine of n times theta. Plus, the other one would be summation, not from 0 to infinity, I'm sorry, 1 to infinity. N equals 1 to infinity. This would be an sine of n times psi. And if those things converge to what they're supposed to converge, this is equal to my f function, an f of theta. And this is also equal to my f function. This is my f of psi. And so when I put back what those psi's, theta and psi's are, I get that my solution that Johann found is 1/2 f of x plus t plus f of x minus t. And that's Jakob's solution. Question? I think Johann showed his brother this calculation, but since he didn't know that Fourier series converged, Jakob was not impressed. But that's an interesting thing to look at. What happens when that x plus t and x minus t leave the interval? And x minus t exit 0 pi. After all, that's where f is defined. That's a fascinating thing to think about, and the key to understanding it is this important observation. About Fourier sine series. Let's see. So Fourier sine series is f of x is the sum from 1 to infinity an sine nx. And the observation is that sine, all those functions are odd, and they're all 2 pi periodic, even when you start multiplying by n, because n times 2 pi is 2 pi periodic. Okay, so I think I drew this picture last time. So that aha is that Fourier sine series converge on the whole real line, not just the interval from 0 to pi, hopefully, R 2. Remember the picture. Let's see, I'll draw a long axis here. Okay, the thing I did last time is I've got f of x right here. First I extended it as an odd function. So to get it as an odd function, I kind of reflect it twice. First I flip it upside down, and then I flip it left to right. That gives me the odd extension. Okay, so this is 0, this is pi, this would be minus pi. And then I extend that in a 2 pi periodic manner. And let's see, so 2 pi periodic would continue and look like this. And this one would go, etc. Okay, so even though we're only concerned on the interval from 0 to pi, that Fourier series converges to that graph there on the whole real line. And notice that graph doesn't have any jumps or anything. That's interesting. It's got kinks. Turns out kinks are okay. They just slow down the convergence a bit. Jumps are interesting. We'll think about them later today. But it converges to that. And then when you think, so I call this extended thing F star. And how did I get F stars? Let me tell you the steps. Steps to get F star. Number 1, extend F from 0 to pi to minus pi to pi as an odd function. And then number 2, extend that. Extend the function you get in number 1 to the whole real line as a 2 pi periodic function. So you just pick it up and repeat it over and over again forever. These are traveling waves, right? So a fascinating thing is the correct version of... So Jakob maybe didn't... he must have thought about how to define his function outside the interval. But so here's the correct version of Jakob's solution, which I did mention last time. Correct version of Jakob's solution, which you can actually check that all those conditions are met. It satisfies the wave equation, it satisfies the boundary conditions, and it satisfies the initial conditions. Is u of xt equals 1/2 the f star thing that you get by doing the odd periodic extension plus the f star of x minus t. And Christina is right. These represent moving waves. This one moves left. So that would take the graph of f that we started out with and moves it left at a speed of 1, actually. If c were in there, it'd be x plus ct, and then it would have speed c, the speed of the traveling wave. This one moves left, and this one moves right. Let's see. I'll show you this neat example in a second. I was proud of myself. I started out with that green thing there. Oh, I should have made it blue, like I did above. I started out with that little green segment, and I figured out a sneaky way to do this extension. Let me move this up a little bit. How did I do this? So we're going to show eventually, quite soon, that Fourier series converge to the midpoint of a jump. Okay, and so those red dots are the midpoint of jumps. But if I start out with a Fourier sine series of a function, that little green thing, here's how I did this graph. I drew this segment. It's pretty crummy looking. Something like that. Okay, so I discovered that using, my program is called Xernal 2.1. Xernal ++ is what it's called. Anyway, if I take this, let me copy that. What? I'm sorry, I shouldn't have done that. I want to control copy and paste. Okay, there's a copy of it. Now I'm going to mess around with the copy of it. Let's see, to get a reflection, I would, first I'm going to reflect it the other way. So I pull this through itself and stretch it out like that. That looks about the right. No, I need to stretch it more. That look about right. Stretch it out. I could do a measurement here and check that. So I flipped it left to right. Now I'm going to flip it upside down. I grab this top one and pull it through itself, and it flips upside down. So, and then I can put it over here. Let's say the x-axis looks like this. Oops. Doggone it. That's supposed to be the x-axis. And now I should, now I can move this. That's the odd extension. Because over here where this is a plus x, this would be minus x, and so this should be f of minus x. This should be this one's f of x. This one here should be minus f of minus x. And right here is the origin. That's the odd extension. Okay. And you'll notice that the midpoint of that jump, when I do the odd extension, is 0. So the midpoint of this jump right here is 0. The midpoint of this jump is right here. And so the Fourier series would converge to that midpoint of the jump. Then when I extend it as a periodic function, the next jump is also 0. So this would be a jump right here. That would be the midpoint of the jump when I do the periodic extension. Okay. So that's pretty interesting to think about. If we know that so the fact is, let's see, so the big fact that we'll eventually fill in the details about is that Fourier sine series converge to f star on R, the odd 2, which is the odd 2 pi periodic extension, of the given f, which is only defined on 0 pi, with the added considerations using, in place of the f, we got to think using values f of x on 0 pi, where f is smooth. And smooth is going to mean that different things the more sophisticated we get. Right now, you might as well take it to C2 smooth. Continuous is sort of not quite enough, which is annoying. Lipschitz smooth eventually will be enough, but we don't want to get too fancy too quick. So you can think of at the smooth places where it looks beautiful, you can do that, where f is smooth, and at places where f has kinks. So those kinks, corners, we'll use f there. But we take the midpoint of the jumps. So we use the values of f of x, where f is smooth and has kinks, but we fill in the jumps. Of the f prime, the f star we get. Giving values that they're the midpoint of the jump. That's what I did in that picture. Then the Fourier sine series converges to that f star. So in the picture, at the smooth places, everything's peachy, converges to the f you get by reflecting and periodic extending. At the jumps that are in the middle of the interval, that's the obvious thing. But you got to think about the jumps that occur because of the weirdness of gluing these pieces together. In the case of Fourier sine series, it's going to be 0 at all the multiples of pi. In fact, if you think about sine, all the sine n pi's would be 0. And so all the sine zeros would be 0. So of course you're going to get 0 there. You don't even have to think about it. But that's the midpoint of a jump in this picture. In fact, that's the basis of figuring out the truth of this matter. Okay, questions about that picture? Read Stein carefully, because he's good at saying these things. I'm saying it more with pictures than he is. He's saying it more with words. So a thing to note here is that sine n pi equals 0 for all n. In fact, for all n in z, including 0. So the Fourier sine series is equal to 0 at all the multiples of pi. At n pi's. And those just happen to be the midpoints of the jumps you get. Okay. Oh, I thought there's a fun thing to see. I made a moving GIF and I put it on in the lecture aftermath page. A fun example. It makes a beautiful moving GIF. Let's see. So I'm going to take a thing with a TP bump. Like that. So how could I get a harpsichord to vibrate with this starting initial condition? I could pin it down. I could hold it like I'm going to pluck it and pin it down at those 2 points and then suddenly let go. then it would start from rest, and my formulas that I get using Johann's method would be valid. And so let's see, if that's going to be the initial condition, then this side would be the odd extension. Let's see if I can do a better job. I could do it exactly with my trick there. That looks almost right. And then the periodic extension would be, let's see, etc. Okay, and so if you think about what happens, if you move that thing to the left and move it to the right and add it together and take the average, here's what the picture looks like. So this is the F star. No, there's no jumps, notice, because there's 0 at 0 and pi. Those are the boundary conditions. So something that satisfies the boundary conditions doesn't have jumps at all. And so they only have to worry about kinks and corners. Yeah, the corners are the kinks. Those are the slow places. And every place else is nice and smooth. So the Fourier series actually converges there. Well, my moving GIF, which you can click on and see, it'll move for you. My initial condition is this. And as soon as it starts moving, this vibrating string, then you get this kind of like a Batman mask that suddenly shows up. Let's see, they'd stay 0 here. And then these Batman masks pull apart more until they're separate. Let's see, they'd be half the size. Okay, so it starts out looking like it's splitting in half. And then this one goes this way, this one goes this way. The height is exactly half the height of the original. And then when they get to the endpoints of the string, they reflect. And so it's kind of funky to see them reflect, but I won't try to do the intermediate ones. You can slow down the GIF and see what actually happens. But it reflects and goes the other way. And then when it comes back together, you get the upside down Batman mask. And then suddenly at some instant, you get exactly the original shape, but upside down. And then that splits apart and reflects and comes back, and eventually comes back and is the original shape altogether. So that's easy to see from the Jakob's solution. Anyway, the moving GIF is a fun thing to play with, and you can find it in the aftermath. So this is the moving. I created that moving GIF in Maple. So that'll get you ready to look at it. And if you slow it down, you can get a pretty good feeling about what's going on. Questions about anything? Let's see. I guess I haven't actually I use Maple to calculate a Fourier series, but a fun example to do that's actually very easy is to find the Fourier sine series for the function that's just 1. So it's 1 from 0 to pi. Well, when I do odd periodic extension, I get a sawtooth function. What is it called? Step function. And it's going to be minus 1 to the left and plus 1 to the right in the odd extension. And then it's going to be periodic, so it's going to be a square wave. And engineers need to understand square waves. It's like turning a switch on and off on an electric circuit. So they certainly want to analyze square wave signals. And the problem is when they try to use Fourier series to do it, they run into some issues. So let's calculate the Fourier coefficients. The AN would be 2 over pi, integral from 0 to pi, of 1 times sine nx. That's easy to calculate. And that would be 2 over pi minus 1 over n cosine nx between 0 and pi. And that's equal to 2 over pi times n times, let's see, minus cosine times n pi plus cosine times 0. Cosine times 0 is 1. But think about cosine n pi. Cosine of pi is minus 1. So that would be, the first one, n equal 1, would be minus 1. Cosine of 2 pi is back up to being plus 1. 3 pi is minus 1. 4 pi is plus 1, etc., etc. And so it's not hard to figure out that this is minus 1 to the n. And so we get this formula, 2 over pi n times 1 minus minus 1 to the n. And 1 minus minus 1 to the n is sometimes 2 and sometimes 0. So in fact, if I wanted to figure it out, it would be 2 over pi. We'd get, oh no, let's see. I'll pull out, it's either 2 or 0. So I'll pull out a 4 here. When it's 2, I'll pull that out and get a 4 over pi times 1. Let's see, what's the first one? Yeah, the first one would be 1 minus a minus 1. That would be the 2. So I get 4 over pi times 1. The next one is 0. The next one, yeah, that's 1 over 1. So I'll put 1 over 1 there. The next would be that's 1 over 3. The next one would be 0. The next one would be 1 over 5. Next one, 0, etc. So this is the n equal 1 spot. Two, 3, etc. And so the Fourier sine series, let's see, I guess I should write out the formula. That's equal to 4 over pi times n if n is odd, and 0 if n is even. That's a famous Fourier series. And let's see if I were going to write it down here. So here's the big question. Is f of x equal to 4 over pi times 1 over 1 times sine x plus 1 over 3 times sine 3x plus 1 over 5 times sine 5x plus ... forever? Well, our harpsichord problem, I got squares when I did this. And they alternated. So the squares meant that I could use the Weierstrass M test and see that the thing converges uniformly to something. Oops, what happened? Sorry. So here's because of the jumps, this is going to converge, but much more slowly. So I'm looking at the coefficients. If I take the absolute values, that would be 1 plus a third plus a fifth plus etc. That's famous series, much like the harmonic series, diverges to plus infinity. So I can't use the Weierstrass M-test to see that the thing converges to something. To see the Fourier series converges. Last time I used it to converge to something. But it does converge by more careful analysis. And on the smooth parts, it converges nicely to the smooth part. At the jumps, it converges to... so the fact is, it does... but slowly. More slowly than the harpsichord pluck. The pluck shape. And that's because of jumps. And so let me say that the picture I did in Maple last time, it looked like this. So let's see. I've got this interval from 0 to pi. Better draw the x-axis. Let's see, then I take the odd periodic extension. That looks like that. And then I take, let's say that's the odd extension. Then I take the periodic extension. So it's a square wave. Etc. And it's fun to, I showed you this Maple graph, the famous one. It overshoots by a certain amount. That's the Gibbs phenomenon. And then it gets kind of close to the actual straight line, and then it overshoots again here, and it overshoots here. Oops. Let's see. Let me see if I can. Okay. It wiggles like this. Okay. And those bumps are Gibbs phenomenon. This bump this overshooting is called Gibbs phenomenon. And it's always a percentage of the it's a percentage of the jump that it overshoots. And let's see, this fact about Fourier series means that the Fourier series would converge to the odd extension. So it would look like this. And it would go to the midpoint of those jumps, which would be at 0. So it does converge at the jumps to the midpoint, but when there's a jump, it overshoots for a while. And if I took more terms in the Fourier series, I could never get rid of the Gibbs phenomenon. It would always overshoot by a certain percentage, but it would get squished. That overshooting part would get squished and smaller. Okay. And that drives the electrical engineers crazy, because it means there's these annoying clicking sounds that are out of whack when they try to use Fourier series to simulate a square wave. They can get close to it, but it's got the Gibbs phenomenon overshoot, which is kind of like a fuzzy noise in a signal. Okay. That's kind of a preview of things to come rather than something I'm being rigorous about today. But to really start studying Fourier series carefully, we need the full Fourier series. I knew a professor at Princeton while I was there. He was the only person I knew, instead of saying the Fourier series, he would say Fourier's series. Nobody says that. Stein said Fourier series. So the full Fourier series, we're going to want to expand f. So I'll put equal here in quotes because it's a big if this is going to converge to f. We're going to need both sine and cosine terms. Okay, the sine terms will be an, and the cosine terms start off. I'm doing this because of Euler's identity. I do the cosine terms first, sine terms second. And like I did with the Fourier sine series in Johann's solution, the key to coming up with what those coefficients must be is that those functions are orthogonal. So let's see, what are the functions? The functions are 1, cosine nx, and sine nx, as n goes from 1 to infinity, etc. N equals 1, 2, 3. That first one is actually the n equals 0 case. Cosine 0 times x would be 1. And sine 0 times x would be 0. So nobody needs 0. Are orthogonal. And let's see, they're orthogonal on a new interval, minus pi to pi. And what does that mean? I guess I'm not going to check. But if I had Maple here fired up, I could easily check that the integral from minus pi to pi of 1 times any cosine nx, that's an easy calculation. Cosine wiggles up as much as it wiggles down from minus pi to pi. Cosine nx does. So you can guess that that's 0, or calculate that it's 0. Same thing would be true if I put here sine nx. So all those other functions are orthogonal to 1 like they should be. Then I got to check. The reason I'm doing this today is you'll see it's kind of agony to write all these out. When we go to complex notation, this will be a much easier thing to check and explain. Let's say I got to check that these integrals are all 0, period. Doesn't matter what n and m are for all n and m. That's a freshman calculus integral you learned at some point, and they told you someday it would be important. This is the day. Unfortunately, you never have to calculate it again. Although it's a worthwhile thing to do, because this is where you realize, oh my gosh, that's an important integral after all. Let's see, that one's done. We need this. Here's what we need. This one. We need cosine nx to be orthogonal to cosine mx. Let's see, that's going to be equal to 0. Let's see, what you can check that when it's n is equal to m, it's cosine squared, and there's a classic freshman calculus way of calculating cosine squared integrals. So it's pi when n is equal to m, and it's 0 when n is unequal to m. And one more. Integral from minus pi to pi of sine nx cosine, not sine, sine n, sine mx dx. Similarly, that's pi when n is equal to m, and it's 0 when n is unequal to m. And lastly, one thing to check is the integral from minus pi to pi of 1 squared dx equals 2 pi. That's a no-brainer. Okay, so how would I figure out what all the coefficients have to be? So the question is, what do the ANs and BNs have to be? I'll illustrate one of them. Let me write f of x. Here's f of x. Here's equal. Let me see if I can be cheat here. Where's my function? Here's my function. Let's copy that. Control copy. Control V. Let me make it black. Okay, I want to figure out how about A3? I'm going to figure out what A3 has to be. Then I would multiply this by cosine 3 times x. I'd multiply this whole mess by cosine 3 times x. Okay, this is my f of x. And then I'm going to integrate from minus pi to pi. Integrate this mess from minus pi to pi dx. When I distribute that cosine 3x through the sum there and do the integral, all those integrals would be 0, except for one of them. So this side would give me equals 0, 0 plus blah, 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 plus the A3 term would be isolated. A3 times something that's not 0. That would be the integral from minus pi to pi of cosine 3x squared dx. And that's equal to pi. Then all the other stuff would be 0. And so that trick spits out that A3 has to be that thing on the left divided by pi. So this calculation reveals that A3 has to be 1 over pi times the integral from minus pi to pi, the function cosine 3x dx. See, I don't think I have time to write all this. I'll start writing it and see what I do. Famous formulas. A naught, when you do this, the constant term is 1 over 2 pi, integral from minus pi to pi of f of x dx. That's the average. The an is 1 over pi, integral from minus pi to pi, f of x cosine nx dx. Now let's see. Maybe I can cheat and get this done. Control copy, Control V. What's the Bn? The Bn is going to be this with a sine and